right, so it should be recording now. All right, so I'm gonna go ahead and get transfer over to my notes. All right, so we have our notes. So we have chapter 11. So chapter 3 is going to be, chapter 11 is inference about two population proportion. So before we get into the inference about two population proportion, we kind of have to get into, because now we're kind of transitioning over from having one population to two population. You are going to encounter where sometimes the population could be an independent sample size or it could be a dependent sample size. So what I mean when it's independent means we have our two population. So we'll say pop number 1, pop number 2, and essentially they don't interfere with each other. So if I pick somebody from population 1, so we'll pick somebody from population 1, it shouldn't affect the person that I choose from population 2. But when they're dependent, and here let me put like independent right here. When we have dependent, essentially we have one population and we're sampling from that population for group number 1. And we're also resampling for group number 2. So when we have population, when we have two different populations, they don't essentially interfere with each other, or if you want to kind of put it as they're mutually exclusive from each other, then you have two different populations. So it will be independent. But if our data set comes from independent, where essentially you're choosing from the same group, and the way you choose somebody from group number 1 interfere on the way how I choose somebody who could go group number 2, that will be considered dependent. All right, so let's go ahead and do some example for this. So for this one says a researcher wishes to determine if alcohol affects one gender more than the other. The researcher conducted a study where they randomly selected 100 male aged 21 or older and 100 female aged 21 or older. They were split up into two groups where both groups were asked to drink 3 ounces of alcohol 30 minutes after consuming the drink. The subject in each group performed a series of tests meant to measure reaction time. So we want to determine if this is dependent or independent. So if you look at this one, we have population 1. And population 1 is essentially what you say is female. Then you have population 2. And we'll say this is male. So if you look at both of these have their separate population. So pretty much since both of them have their separate population, we're going to be selecting from population female to get group number 1. And we're going to be selecting from population male to get group number 2. So if you kind of look at that, these two will be considered independent events because the way I choose the female shouldn't interfere with the way I choose the male because they're independent from each other because they're in two separate groups. All right, but that's the first example. So for this one, you should say independent. All right, so let's do the second one. So if you look at this one, it said a researcher conducted an experiment to see if specific eye exercise can improve peripheral vision. A random sample of 5 people were rated for peripheral vision on a scale from 1 to 20, where 9 is considered average and higher score indicate better peripheral vision. Then they follow the prescribed eye exercise program and were rated again. So if you look at this one, we have two groups. We have pre-eye exercise. So we have pre-eye exercise, and then we have post-eye exercise. So those are the two groups that we kind of want to put them into. We want to put them before they take the eye exercise, and then we want to test them again after they take the eye exercise. So for this one, would it be smart if they get like one, so say we have these two populations. So would it be smart for them, population number 2, to get somebody for population 2 to take the eye exercise, and then get somebody from population 1 to do the to do the exam without doing the pre-exam? Would that make sense? Cool, so I gotta know. Yeah, so it wouldn't make sense because essentially what you want one person taking the pre-exercise exam, and then you want somebody taking the pretty much the post-eye exercise exam. Okay, you want to see if the exercise exam work. So you don't want this population. Essentially, what we want to pick a person. Once we pick that person, they're gonna take the exam pre-exercise exam, and then they're gonna take it again post-exercise exam. So we want to see if this actually works. So if you look at this one, we're only sampling from one population, but once we sample from that one population, that person goes to both group. It goes to the pre-eye exercise and the post-eye exercise. Usually for this, they call this a before and after. Because essentially you have a before group and then you have the after group. So in this case scenario, this will be considered a dependent data set. Everybody good on dependent data set? All right, excellent. All right, last one. So for this one said, do women tend to select a spouse who have a IQ higher than their own? To answer the question, research randomly select 20 women and their husband. They measure the IQ of each husband wife team to determine if they are significantly different in IQ, determine whether the sampling is dependent or independent. All right. So if you look at this one, do you want to know if women tend to select a spouse who has a higher IQ score? So what they want to do, we're going to call them spouse 1 and spouse 2. So we have spouse 1. And we have spouse 2. So for this one, kind of imagine we have our two populations. So say we randomly select all married couple for this one population. And then we compare, we get these other population of married couple. And then we randomly select one person to go here. And then we randomly select somebody from that population to go here. And then what we're gonna do, we're gonna compare their IQ scores. So would that make sense to do it like that? Well, if you kind of look at it, they want to compare to see if a woman tend to marry somebody who has a higher IQ score. So if I randomly select somebody who's not married to the other person, does that really tell me if the woman actually marries somebody who has a higher IQ score than them, if they're not married to each other? Because pretty much for this one, what you want to do, you only want to pretty much sample from one population. So you're going to be looking at population of married couple. Yeah. We have to do that spouse. Because what you want to do, you want to pretty much get a population of all people who are married. So once you get that population of people who are all married, what you want to do, you want to randomly select a couple. But the thing is, once you randomly select that couple, one of them will go into this group, the other one goes into that group. So if you kind of notice for this one, you don't have two independent population because you're essentially sampling from one population, and from that one population, you're getting the two group. Because this is something that they call a match pair design. And this will also be considered dependent. Yeah. So for this one is a match pair design, and this one will be considered a dependent data set. So if it's match pair or if it's before and after, that's kind of your clue to tell you that this is something that's considered a dependent data set. But if we have two different populations that we're sampling from, that will be considered a independent data set. Any question in regard to that so far? All right, no question. All right, so let's get to the formula, the fun part. All right, so pretty much for this one, since you have two different population, you're essentially gonna have two formulas for each population. So if you look right here, you have p hat of 1. So that's your sample proportion for population 1. Then you have p hat of 2. P hat of 2 is your sample proportion for population number 2. So when you see the subscript 1 and the subscript 2, essentially what that means is telling you it's population 1, population 2. If you want, you could change that from 1 and 2. So say like for the last one, where we're doing like husband and wife. So if you wanted to, you could say P hat of H, P hat of W, if that would make it easier for you. But the 2 and the 1 just correspond to which population they're in. But you could always change that to kind of adapt to what it actually is. All right. So that's your P hat of 1, and that's your P hat of 2. Also, there's something called mu P hat of 1 minus P hat of 2. So in this one, what you're calculating the difference of the two proportion. So you're seeing like how much of a difference you have from both of them. So if one of them is 0.5, the other one's 0.4. If you subtract both of them, 0.5 minus 0.4, you get 0.10, and that will be your answer. All right. But any question for mu p hat minus p hat of 2? All right. So up next, we're going to go ahead and find the pool estimate of population proportion. So the pool estimate is p hat. So this p hat is a little bit different from the p hat of before, because p hat we just x divided by 1. In this case, p hat will be x1 plus x2 divided by n1 plus n2. So it's pretty much just these two added together. And then what we're going to do with that p hat, we're going to find the standard error, which is over here. So the standard error is equal to square root of p hat times 1 minus p hat multiplied by square root of 1 divided by n1 plus 1 divided by n2. And lastly, we're going to get the test statistic by doing p hat of 1 minus p hat of 2 divided our standard error. And that's how we're going to get the z value. So it shouldn't be that bad. Any question in regard to the z value? All right. So up next, we have the central limit theorem. So remember, the central limit from before was you have to have a large sample size and you have to have a big population. So the thing still is the same. You have to have a big population. You still have to do a large sample size. The only thing that's different now, since you have two population, you have to do it for both populations. So you have to do it for population 1, but you also have to do it for population 2. So if you look right here for large sample size, that's the formula for large sample size, or sorry, for big population for population 1. Here's the formula you're gonna have to check for your second population. So for population number 2, you do 20 times n2, and that has to be less than or equal to n2. And remember, n is capital N, just represent the population proportions, or the population sample size, sorry. All right. So that's how you check big population. So it's still the same as before. The only thing different, you have to check for both population. All right, so for large sample size, you have to do n1 times p hat of 1 times 1 minus p hat of 1, and that has to be greater than 10. So this is for population number 1. For population number 2, you have to do n2 times p hat of 2 times 1 minus p hat of 2, and that also has to be greater than or equal to 10. So if you look at it, it's pretty much the same thing. The only thing you have to do, you have to adjust it to that now you have two population versus before we only had one population. So you have to do twice as much as before. So that's your central limit theorem. Any question for the central limit theorem? All righty then. So let's go up here. All right. So if you look at the table is showing the different way that you could do the null and alternate hypothesis. So for this one, it is slightly different from before, because before the left side had your parameter. On the right side, it had a number. For this one, sorry about that. For this one, the left side and the right side are not going to have any number. It's going to have the parameter. So the left side going to be P1, the right side going to be P2. But the only thing that's going to change for the alternate hypothesis, you're either going to say P1 is not equal to P2, P1 is greater than P2, and P1 is less than P2. But for this one, there shouldn't be any number in any of the null or alternate hypothesis. It should all be either P1 or P2. The only thing is changing is the inequality. Any questions so far? Great. All right. So for this problem, we're going to do this. This actually came out of a TV show. And what we want to do, we want to pretty much say if the TV show got it right. Because when the TV show did it, they said there was a significant difference. So for them, they came up with the conclusion that yawning was contagious. So first thing we want to kind of see, did they do a valid statistical design experiment? And also, do we also get the same result that they got? So for this one, it says Mythbuster is a popular television program on the Discovery Channel once conducted an experiment to investigate whether or not yawning is contagious. The premise of the experiment was to invite a stranger to sit in a booth for an extended period of time. 50 subjects were said to be tested in total, of which 34 was seated with a yawn by the person conducting the experiment. The other 16 were not given a yawn seat. Using a two-way mirror and a hidden camera, the experimenter observed and recorded the results were given below. All right. So pretty much what was happening here. So in total, they have 50 people, but they had 34 people who were seated with a yawn, and they have 16 people who were not seated with a yawn. So what I mean by seated with a yawn, so kind of think about it, they had 34 people in a room, but of the 34, they had this additional person, and this additional person worked for them. So they wanted to see if this person started yawning, would that make the other 34 people also yawn? So when it says seated with a yawn, that means they have somebody in their crew in the group, and that person actually started yawning first. And then they wanted to see if that will pretty much make yawning contagious for the other 34 people. So then you have the second group, which says not seated with a yawn. So not seated with a yawn means essentially nobody in the crew were in that group. They just want to see if they would just naturally start yawning by themselves. All right, so the research question that we want to answer is, does the data provide statistical significance or statistical evidence that those seated with a yawn are more likely to actually yawn at a 10% level? All right, so let's go ahead and do this one. So we're gonna first describe the parameter that is being tested. So what is the parameter that is being tested? Well, the parameter being tested is the proportion All right, so that's the proportion. So the proportion of people who yawn in the seated and non-seated group. So that's your parameter. So a little advice, like anytime it says parameter, pretty much I want you to tell me if this is the mean, which mean is mu, if it's proportion, which is P, and I ran out of space, so sigma, which is standard deviation. So like anytime I ask you in a sentence, describe the parameter that being tested, if anywhere of that sentence you don't see the word proportion, mean, or standard deviation, there's a good chance that might be considered wrong, because in order for it to be considered a parameter, it has to be one of those three. So that's what I'm looking for when I say in a sentence, describe the parameter that's being tested. Somewhere along that sentence, it should say like we're testing the parameter of proportion, the parameter of the mean, the parameter of standard deviation, but it should say something like that. All right. So let's go ahead and fill this one out. So let's go ahead and decide which one do we want to be group number one, which one do we want to be group number two. So which one do we want to be group number one, seated with a yawn or not seated with a yawn? And it really doesn't matter which one we label which. Cool, perfect. So this is CETA. So that's group 2. So CETA will be group number 1. Not CETA will be group number 2. All right. So let's go ahead and do N1 and N2. Let's do the easy stuff first. So what's my N1? How many people participated in CETA with a yawn? So group number 1. Oh, 34. All right. How many people were not seated with a yawn? Wait. All right. So far, 2 for 2. Of the people in group 1, how many of them were yawning or yawn? Oh, 10. Of the people in group 2, how many of them yawn? On a row. All right, so now we're gonna do p hat of 1 and p hat of 2. So p hat of 1 is 10 over 34. P hat of 2 is 4 over 16. So I could actually do 4 over 16 in my head. This is 0.25. Let's do 10 divided by 34. See what do we get there? 10 divided by 34. You get 0.294. Yeah, we'll leave it at 4. All right, so that's it for step number 4. So step number 4 is there to kind of help you out and pretty much, oh, no, we still need p hat. So let's do p hat. So if you look at p hat, so you get x1 plus x2. So x1 plus x2 is 10 plus 4. Now it says you divide that by n1 plus n2. So that's 34 plus 16. So that's 14 over 50, which is 28 or 0.28. All right, now we are finished with step number 4. Any question in regard to step number 4? All right, so let's check some assumptions. So, because if you look at the problem, nowhere in the problem does it say that the data set was normally distributed. So let's go ahead and see if they got a big sample size or also if they have a big population. So let's check the CLT. So let's check big population. Let's check large sample size. All right, so remember for big population, we have to check to see if the population is big. So for this one, if you kind of look at it, they didn't really have like a particular person that they wanted to get. So essentially what we're gonna do, since this study was done in America, we're gonna say pretty much our population are all American. So that's our population. So let's do N. Which population do you want to do first? Population 1 or population 2? All right, population 1 it is. So we go with pop number 1. So for population number 1 is 34. So we're gonna do 20 times 34. So if I do 20 times 34, you get 680. So now we have to see, is that smaller than the population of, and for this one where you're saying American, so is that smaller than the population of American? So are there more than 680 American? Cool, so we'll say yes. All right, let's go ahead and do population 2. So we do 20 times 16. I think if I do that on top of my head, that's 320. All right, so are there more than 320 Americans? So the answer for that should also be yes. So far for the big population in clear, because obviously our population has more than 320 and 680 respectively. All right, so let's do our large sample. So for our large sample, what we're gonna go ahead and do, we're gonna go ahead and do N1 times P hat of 1 multiplied by 1 minus P hat of 1. So N1 is equal to 34. P hat of 1 is equal to 0.294. And we do 1 minus 0.294. So I'm gonna go ahead and work that out. So we do 34 times 0.294 multiplied by 1 minus 0.294. You actually get 7.057. So if you look at that, that's definitely not greater than 10. So for population 1, based off of this, they didn't sample enough. So they should have had a bigger sample for population 1. Well, let's check population 2. Maybe in population 2, they got it straight. So for population 2 will be N2, which is 16, times 0.25 times 1 minus 0.25. So let's do 16 times 0.25 times 1 minus 0.25. Oh, that's even worse. So you get 3. So if you look at it for this sample size, they actually didn't get a big enough sample size. So anything that we get from this study is essentially pretty much non-useful for us. Because in order for it to be useful, we do have to have a big population, but also more importantly, you do have to have a large sample size. And what this is telling me that the sample size is not big enough. So that means anything that they get from this study is non-trustworthy. So any conclusion that we make for this one is also non-trustworthy because the sample size was so low. But just for you could get a feel of how to do the testing, we're going to continue on with it. So we'll say does not pass the large sample size. All right, so let's go over the null hypothesis. So for the null hypothesis, that one is super easy. You put P1 is equal to P2. So you say the proportion of people who yawn in group number 1 is the same as the proportion of people who will yawn in group number 2. So for my alternate hypothesis, we'll put P1, P2. But for this one, which group do I think will yawn more? People in group number 1 or people in group number 2? Yeah, good. Group number 1. All right. So that's my alternate hypothesis. Any question for the alternate hypothesis? All right, so up next, I'm going to go ahead and do step number 5. Step number 5 is a process that you need to do in order to get the test statistic, which you were quizzed on today. So let's do P hat of 1 minus P hat of 2. So that's going to be 0.294 minus 0.25. That would give you 0.044. So you get 0.044. So that's how much of a difference that we have. So we have a 4% difference between P hat of 1 and P hat of 2. So we want to see that's significant. So up next, we're going to do the standard error. So for the standard error, we're going to say square root of 0.25, or sorry, 0.28 times 1 minus 0.28. Got them mixed up. And we're going to multiply this by the square root of 1 divided by n1, which is 34, plus 1 divided by n2, which is 16. Any question in regard to that so far? All right, so I'm going to go to my TI. And let me take you on that ride with the TI. So that way you can see how to input it. So for this thing, you go second, square root, and then you go 0.28. And then you could do parenthesis, 1 minus 0.28, loads parenthesis. Let's go on to something new. And then you open up a new radical, and you say 1 divided by 34 plus 1 divided by 16. And then you press enter. And that's our standard error. They get 0.136. So if you look at the standard error is pretty high because that's telling you like one standard deviation is roughly 13%. So if you look at it, since it's telling you that one standard deviation is roughly 13%, and we got a difference of 4%, that's not even more than one standard deviation away. So we should get a pretty small z value. So we're going to say 0.044 divided by my standard error, which is 0.136. Cool. So up next, what we're going to do, we're going to let the calculator do the work for us. So we're going to let it get the test statistic for us, and we're also going to let it get the p-value for us. So I'm going to go to stats. I'm going to go to test. And if you look right here, if you remember from chapter 10.2, we use one prop z-test. In chapter 11.1, we're going to use two prop z-tests because we're switching over from one population to two populations. So I'm going to go to number 6. All right. So if you look at it, that's going to be for x1. x1, we're going to say is 10. And 1 is 34. x2 is 4. And 2 is 16. If you look at this one, they're asking which of these three do we want to choose? We want to choose greater than because that's what we said for H1. And let's go ahead and calculate. All right, so if you look at my z-value is 0.324, 0.324. All right. If you look at it, it also gave me the p-value right below it. The p-value, if you look at it, that's a pretty high p-value. So it's kind of telling us like by random chance, the probability that we get this 4% difference is a 37% chance of occurring. So that's pretty high of occurring. So it's kind of telling us like this is something that usually happens normally. If it was something closer to 0, then that's something abnormal. But for this case, it's very normal. All right. So for this one, what type of tail test would this be? Would this be a left tail test, a right tail test, or a two tail test? Cool. So remember, for this one, you have to look at the arrow. The arrow is pointing to the right-hand side, so this is the right tail test. So for this one, we'll say right tail test, we'll say 0.373. All right, so let me go ahead and switch over to my notes. All right. So if you look right here, the only thing I put right here was my test statistic. So my test statistic was 0.324. And then down here, I put my p-value and that this is a right tail test. So there goes the p-value, there goes the p-value, and there goes the right tail test. So let me go back and let's go find the alpha. So if you look for the alpha, we chose this to be, oh, here goes the alpha. Alpha was 10%. So we'll say 0.10. So which one is bigger, p-value or alpha? Oh, p-value. So since p-value is bigger, which is this one, we select this one. So if you look at it, it says fail to reject. So anytime it says fail to reject, anytime it says fail to reject, that means there is not enough evidence to support the claim that the proportion of people and, so here you go. So it says there is not enough evidence to support the claim that the proportion of people who yawn in the seated group is not greater than the proportion in the not seated group. In short, yawning is not contagious based on this evidence. And that's it for that last problem. So if you look at it, it has a very familiar feel to chapter 10. The only thing is there are some slight little difference between it because pretty much you have to just do two population versus you're doing one population. But you kind of know like the process is still the same. You still find all of these steps. And once you find all of these steps, it should help you be able to figure out if you should say there is enough evidence or there's not enough evidence. No. Yeah, give me a minute. Yeah, I think the person said that people probably went to the Laker game. Well, they can't go to the Laker game, or I got ditched by the Laker for the Laker game. Yeah, apparently the Lakers are playing the Clippers, so that explains the low turnout. I wonder if there's a correlation. Yeah. Any question in regard to this last problem? All right. Let's move forward. Up, up, and beyond. So for this one said, suppose the acne drug company develop a new drug designed to prevent cold. The company states that the drug is equally effective for men and women. To test this claim, they chose a simple random sample of 100 women and 200 men from a population of 100,000 volunteers. At the end of the study, 38,000 of the women caught a cold and 51% of men caught a cold. Based on this sample, based on these findings, can we reject the company claim that the drug is equally likely or equally effective for men and women? Use a 0.05 level of significance. All right. So for this one, who are my two populations? Remember, whenever I'm asking for population, there should be no numbers involved. There we go. So it should be men and women. And it should never say, if I ask the sample of each sample or each population, then you say 100 and then you say 200. But anytime I want the population, you tell me, hey, it's men and women. All right. And what are we trying to test? What are we trying to test in regard to these two populations? Well, what we're trying to test, we're trying to see if this drug is equally effective for both men and women. So we'll say, oops. Not group. All right. So we'll say the proportion of women who took the drug and caught a cold is the same as the proportion of men who took this drug and caught a cold. So pretty much we have our two population, but you have to kind of make it easier. So we have women, which is population 1. So we'll say this is population number 1, numero uno. And then we have men, which will say the population dos. So anytime you see like N1 is referring to women, N2 is referring to men. So you just always make sure you just label them as 1 and 2. All right. So everybody good for my sentence to describe the parameter that we're testing? All right. And just remember for this one, I know it's correct because if you look at it, I'm saying the word proportion. So I'm describing the parameter that we're testing. All right. So let's do, well, let's not do the null alternate hypothesis right now. Let's do part number 4. So for part number 4, so what's my sample size for women? Oh, 100. There we go. What's my sample size for men? 200. All right. So for this one, my sample size of men, or sorry, of women, if you look at it, they don't give me what X1 is, but they actually give me what P hat of 1 is. So what's P hat of 1? So how many women caught a cold? 38. What percentage of men caught a cold? Yeah, so 0.51. All right, everybody good how we got 0.38 and 0.51 for P hat of 1 and P hat of 2? All right. So up here, we're gonna do X1 and N2, well, sorry, X1 and X2. Like you really want to find X1 and N2 because if you want to use your calculator, you're gonna need X1 and X2. So we need to find this with our calculator or for our calculator. So to find X1, all you have to do is say, hey, get 100 times 0.38 and you get 38. If you want to find X2, you say 200 times 0.51 and you get 102. All right. And we're still not done with 4 because we still have to find p hat. All right, everybody good so far? I got x1 and x2. All right, let's do p hat of 1, or sorry, p hat. So for p hat, what you do x1 plus x2. So that means we do 30a plus 102, all divided by 100 plus 200. So you get 30a plus 102, you get 140. And then you do 100 plus 200, that's 300. So now we do 140 divided by 300. We get 0.4667. All right, so we're all done with p hat of 1. Everybody good with p hat of 1? So let's go ahead now. We're gonna go to step number 1. We're gonna check our assumption, because for this one, if you know it, they don't tell us it's normally distributed. They kind of leave us hanging on the wind because they don't tell us this is normally distributed. So what we have to do, we have to use the central limit theorem. And what we have to do, we have to check to see if we could say this is approximately normal. So the way that we could check to see if it's approximately normal, we had to check for large sample size. But we also have to check for big population. All right, so let's go ahead and do this one. So for large sample size, what we have to do, we have to look at each individual population. You see, was the sample size that each population had, was that a significant amount? So to be able to do that, we're gonna say n, which is 100. So I'm doing population 1 right now. And then I'm gonna multiply that by 0.38, and then multiply that by 1 minus 0.38. So if I go ahead and do that, I do 100 times 0.38 times 1 minus 0.38. All right, we get 23.56, which is definitely greater than 10. So for my first population, we did have a large sample size. I want to see the second population, did they also have a large sample size? So let's do that in a different color. We'll do it in blue. So we'll say 200 times, what was there, 0.51 times 1 minus 0.51 is equal to, so let's go ahead and do this, 200 times 0.51 times 0.49. You get 49.98. So if you look at 49.98, it's definitely bigger than or equal to 10. So we could say we have a large sample size. So the large sample size have been checked off. Up next, we're going to do is big population. But any question in regard to large sample size? All right, so let's do big population. So for big population, we have to get 20 multiplied by n1, and that has to be bigger than the population. In this case, they told us that the population was 100,000, so we don't have to theoretically think about it. All we have to do is just look at the 100,000 and you see, is it bigger than 100,000? Or sorry, is it smaller than 100,000? If the answer is yes, then we have a big population. So we'll say, so first I'm going to do the men, or sorry, women. So the women with 100 times 20. So if you do 100 times 20, that's 2,000. So if you look at 2,000, we know our population is 100,000. So that one checks off. So far, so good. Now we're going to do the men. So for the men, we'll do 200 times 20, which is 4,000. And if you look at 4,000, it is definitely smaller than 1,000 or 100,000. So we do have a big population. So we say this is approximately normal. And that's it to check the assumption. Any question in regard to how we check those assumptions? All right, so let's get to number 5. All right, so for number 5, what we're gonna go ahead and do, we're gonna check to see if our test statistic, which in this case is our z-value, is our z-value significantly big? So let's first do mu of p hat of 1 minus p hat of 2. So we're gonna do p hat of 1 minus p hat of 2. So p hat of 1 is 0.38 minus 0.51. There we go, 0.38 minus 0.51. You get negative 0.13. So that's mu of p hat of 1 minus p hat of 2. So if you look at it, we have a difference of 13%. So we're trying to find out, is that difference of 13%, is that something that's significant? Or did that just happen by random chance? So next we're gonna do the standard error. So for the standard error, we're gonna say square root of p hat, which is 0.4667 times 1 minus 0.4667. And then you multiply that by square root of 1 divided by n1, which is 100, plus 1 divided by n2, which is 200. So for this one, I'm going to run out of room, so I'm going to do that down here. So let's do this in the TI-84 so that way I can show you how to do it. So we'll say square root of 0.4667. That's weird. 0.4667 parenthesis 1 minus 0.4667 close parenthesis. I'm going to move this over and we're going to multiply this by second radical 1 divided by 100 plus 1 divided by 200. And you enter it, you get 0.06. You get 0.0611. So we just found the standard error. So we get negative 0.13 divided by 0.0611. So here, let me just take you back to my notes. All right, so this is what I found, 0.0611. So if you look at the standard error, it's saying on typical, we should expect pretty much a standard deviation of 0.06. So that's kind of telling you like how far off we could go. But if you actually look at the difference is telling us we have a 13% difference. The standard error is telling you typically we only have 6% of difference. So most likely this 13% difference is significant because the standard error is lower than it. But let's actually do this in the calculator. For that we can see what do we get with the calculator. All right, so if we do this with the calculator, we go to stats, we go to tests, we do 2 prop z-tests. So if I do x1 is 38. If I do n1 is 100. x2 is 102. n2 is 200. Oh, and for this one, we forgot to do the null and alternate hypothesis. So for this one, the null hypothesis should be that P1 is equal to P2. But what should the alternate hypothesis be? Should we say that the proportion of men get thicker or get a coat more often than the other? Well, for this one, you want to put not equal to, because essentially we just want to prove that they're different. because pretty much the drug is trying to claim that they're the same, but we don't really care if one gender gets sick more than the other, because essentially what we want to do, we just want to prove that it's not equal, like the drug doesn't work as well for both gender. It's essentially one gender will still get more sicker with this drug. So you want to say not equal to. All right, so we'll select not equal to, and we'll go here, calculate. All right, so that's my Z value. So my Z value is negative 2.127. Right. If you look at the p-value that we get is 0.0334. All right. But if you look at it, we got the p-value and we got the test statistics. So I'm gonna go back to the notes and we'll finish this problem off. So if you look at the problem, they tell us we want a 0.05 level of significance. So we put it there. So which one's bigger, my p-value or my alpha? Alpha of 0.05 or p-value of 0.0334? Alpha, perfect. So since alpha is bigger than p-value, you want to say we reject the null hypothesis. So we reject the null hypothesis. So we want to say there is enough evidence to say that is not equally so for this one, we want to say there is not enough evidence to say that the drug is not equally effective or is. I'm sorry about that. So we want to say there's not, there is enough evidence to say that the drug is, I was right the first time, not equally effective for both men and women. And that's it for that second problem. Any question in regard to the second problem? All right, so I'll leave it there just a minute, just in case you need to write something down or anything like that. All right, so let's go ahead and do this next one. All right, so for this one, say extra practice. Let's get some extra practice. So for this one, say, let's say you're testing two flu drug A and B. Drug A work on 41 people out of a sample of 195. Drug B work on 351 people in a sample of 605. Are the two drug comparable? Use a 5% alpha level. All right. So for this one, if you look at it, you have drug A and drug B. This should be capitalized. So we have drug A. So we're gonna say this is population 1. We have drug B. We're gonna say this is population 2. So what we want to check out for this one is essentially, do you want to see if this blue drug is equally effective for both, like is it the same for both of the drug, or is one drug more effective than the other drug? So for this one, we'll say innocence is described as the parameter being tested. Right. So innocence is described the parameter as being tested, the proportion of people who get the flu while using drug A and drug B. All right. So for this one, for that way I won't forget, let's do the null and the alternate hypothesis. So the null hypothesis should be that both of them are equally as effective as the other one. So there's no difference between drug A and drug B. The percentage of time that drug A worked is the same percentage of time that drug B worked. So for the alternate hypothesis, we're gonna say P1, sorry about that. So we're gonna say P1 and P2. So which symbol should I put in between if they want to show that the two drugs are comparable? Well, for this one, kind of like the last one, since they want to see they're comparable, all we want to prove that they're not comparable. So you put not equal to. So for this one, since they didn't really give us any indication that they think drug A or drug B work better, essentially what we're gonna say like, okay, they're just not comparable. So for the null hypothesis is they are comparable, but for the alternate hypothesis, we're gonna say that the two drugs are vastly different. All right, so let's go ahead and let's do step 4. So for step 4, we're gonna do N1. So N1 is the sample size for drug A. So if you look at drug A, they had 194, well, 195. If you look at drug B has 605. If you look at drug A out of the 195, 41 of them, pretty much it worked on 41 of these 195. And then for drug B, it worked on 351. So now if I want to do P hat of 1, P hat of 1 will just be 41 divided by 195. 41 divided by 195. And you get 0.2103. And we want to do P hat of 2. P hat of 2 is 351 divided by 605. This is 351 divided by 605. You get 0.5802. All right, just by looking at it, you might guess that there is a significant difference. Because if you look at one drug, it worked on 21% of the time. If you look at the other drug, it worked 58% of the time. So for this one, there should be definitely something that's saying that they're not comparable. They're pretty different on how effective each one of them are. But in case you don't see that, let's continue going. So we're gonna say P hat. So P hat is X1, which is 41 plus 351, all divided by N1, which is 195 plus 605. So let's do that. So you do 41 plus 351, that's 392 divided by 195 plus 605, and you get 49% or 0.49. So up next, we're gonna go. So for this one, we're gonna skip the assumption. Hopefully you kind of understand how to get the assumption now. So we're gonna skip to step number 5. So we're gonna do mu p hat minus mu p hat of 1 minus p hat of 2. So we're gonna do p hat of 1 minus p hat of 2. So p hat of 1 is 0.2103 minus 0.5802. If I do that, you actually get negative 0.3699. So roughly there's a 37% difference. So there's a huge difference between one drug and the other drug. So there's a difference because drug B worked 58% of the time, drug A only worked 21% of the time. All right, so let's do the standard error. So to calculate standard error, we say square root of 0.49 times 1 minus 0.49 multiplied by square root of 1 divided by N1, which is 195, plus 1 divided by N2, which is 605. So let's go and do that problem. So we'll say square root of 0.49 multiplied by 1 minus 0.49. Then you press this arrow, you have to get outside of the radical. Oops, I forgot to close the parenthesis. Now get outside of the radical. And then if you want, you could hit multiply radical 1 divided by 195 plus 1 divided by 605. Press enter. And you get 0.04. Negative 0.3699 all over 0.04. So if you look at this, just by looking at it, you should kind of tell you're gonna get a huge C value. Okay, if you look at the standard error is telling you is 4%. And our difference between p hat of 1 and p hat of 2 is 37%. So we should be getting a big Z value just because our difference and the standard error that it should be, there's a vast difference between it. So I'm gonna go ahead and just do this on the TI-84 right now. So we're gonna do 2 prop Z tests. So X1 is gonna be 41, N1 is gonna be 195, X2 is 351, N2 is 605. Like our p-value should be very close to 0, and then we're gonna put not equal to. Let's go calculate. All righty then, so yeah. So if you look at our Z value, you get negative 8.99. If you look at our p-value, you get 2.603813. But if you look at it, it says e to the negative 19. So that means you get the decimal place and you move it 19 places to the left. What we're gonna do, we're gonna say this is 0, because if you round it off to 4 decimal places, you get 0. All right. So for my Z value, we get negative 8.99. For my P value, we get 0. And for this one, we're going to say this is a two-tailed test. Any question in regard to that so far? All right, so let me go ahead and transfer back. All right, so I put the negative 8.99 here. I put p-value 0, p-value 0, and we have a two-tailed test. So no matter what my alpha is, any alpha I choose should be bigger than 0. So let's see what alpha did we get. If you look at it, we got a 5% alpha level. So you get 0.05. So if you look at 0.05, if you look at 0, 5% should be bigger than 0. So for this one, we'll say reject. And for this one, you want to say there is enough evidence to show that the two drugs are not equally effective. All right, and that's it for our last problem. All right, how do we feel about hypothesis testing for two population parameter or two population proportion? Cool, so we're good. All right. So we're gonna do, there's this other problem. If you want, you can practice on it. You have to kind of get more practice on it. It's kind of crazy one. So if you want, you practice on that one. But let's actually move on to this one. All right, so if you kind of remember back when we did chapter 9 and we did 9.1, we did confidence interval, but we also said like how big of a sample size do we need if we had a margin of error and a confidence level of a certain size. So for this one, we also have that thing. So we also have like how to determine how big of a sample size do I need for both population in order for us to have a certain margin of error, but also a certain confidence level. So here are the two formula we're gonna use. So one of the formula is when we know the proportion for both population, which is the first formula. And if you look at the second formula, if we don't know the proportion for both of those proportion. So the first one is if I know the proportion for both of them. The second formula, if we don't know it. So I'll give you a minute in case you're writing it down or anything. Cool. All right, so let's use these two formulas. So for this one said a doctor wants to estimate the difference in the proportion of 15 to 19-year-old mother that received prenatal care and the proportion of 30 to 34-year-old mother that received prenatal care. She used the results of a national vital statistic report result in which 98% of the 15 to 19-year-old mother received prenatal care and 99.2% of 30 to 34-year-old mother receive prenatal care. So first thing you want to kind of determine which are my two populations. So the two populations are 15 to 19-year-old mothers. Ooh. And then you have, what was that? 30 to 34 year old. So those are my two population. So if you look at my two population, do they give me the proportion of 15 to 19-year-old and 30 to 34-year-old who use prenatal care? Yes or no? Or a maybe? Cool. So they do give me that. Cause if you look at for 15 to 19-year-old, they tell me that's 98. There is a p hat of 1 is 0.98. P hat of 2 is 0.992. Like anytime you're doing these type of problem, like the first thing that you should always do is just label all the number. So that way, once you actually go into the problem, you already know like, okay, I already know what p hat of 1 is, I already know what p hat of 2 is. So that way you could start just substituting everything in. So if you look at part A, it says what sample size should be obtained if she wishes the estimate to be within 2 percentage points with a 95% confidence, assuming that the data is normally distributed. So the key thing is they tell me right here what sample size should be obtained. So that's telling me we're looking for n. So that's automatically telling me we're going to be using one of these two formulas. So for this one, which formula should I use, the top one or the bottom one? Cool, perfect, yeah. So we're using the top one. The reason why we're using the top one, because for this one, we know our population proportion for each population. We know for 15 to 19-year-old mother is 0.98. We know for 30 to 34-year-old mother is 0.992. So that's why we're using the top one, not the bottom one. Okay, so if you look right here, it says within 2 percentage points, that's going to be your margin of error. So 0.02. Remember, for this one, if it says 2 percentage points, that means 2%. 2% is 0.02. Up next, they give me 95% confidence. So that means confidence level, or CL, is 0.95. But if you look at the formula, we want to get Z alpha divided by 2. So in order to find alpha, we do alpha is equal to 1 minus 0.95, which is 0.05. Then you do alpha divided by 2, which is 0.05 divided by divided by 2, and you get 0.025. So what we're going to do, we're going to find Z of 0.025. Any question for Z of 0.025? Or how we found the 0.025? All right, so just remember, the way that we find this Z value, you have to use our calculator. So we're going to use inverse norm. And you put 0.025. And that will give us our Z value. And I essentially just ran out of space and we still haven't done the problem. All right, so let me go to the calculator, show you how to do this on the calculator, for that way you can get the Z value. So you go second, you go VARS is to the left of clear. You go all the way down to 3 where it says inverse norm. If you look at it, it says area is 0.025. You click, and you get 1.95996. So that's essentially going to just round up to negative 1.96. But remember, for this one, always just convert it into a positive. Because if you look at the formula, say you're going to square our Z value. If you square negative, you can become a positive. So you get 1.96. All right, so let's go ahead and switch back to my notes for that way we could just finish off this problem. All right, so if you look right here, here goes the 1.96. Well, here goes the 1.96. So for our formula, we're gonna say, is it doozy? We're gonna say 0.98 times 1 minus 0.98 plus 0.992 times 1 minus 0.992. You close the bracket and then you put z. Z is 1.96, all divided by my margin of error, which is 0.02. And don't forget to square this. Any questions so far on the substitution into the formula? All right, so let's go back into our TI-84. And now we have to calculate this fun thing. So anytime you see a bracket or parenthesis, just use a parenthesis. So we're gonna say parenthesis, 0.98, close parenthesis, open parenthesis, 1 minus 0.98, close parenthesis, and then you say plus, open parenthesis, 0.992, close parenthesis, open parenthesis, 1 minus 0.992, close parenthesis, and then you close it again because you're essentially closing all of that off. And then you open up a parenthesis, you do 1.96, and you divide this by 0.02. You close that parenthesis and you put that to the second power. And we are done. And that's your answer. And if you remember for this one, the same thing go for the same thing go for when we did this in chapter 9, where for this one you always round it up to a whole number. So for this one, if it's just to say 264.4557, you round this up to the next whole number. So the next whole number will be 265. So your final answer will be 265. So if you look right here, here's my final answer. So what this final answer represents, telling me how big of a sample size do I need for not one population, but for both populations. So it's telling me for population 1, I need 265 sample, but it's also telling me for population 2, I need a sample of 265. So for both of them, I need a minimum of 265 or above. If I get 265 or above, that's gonna mean I'm gonna have a 95% confidence level with a 2 percentage point margin of error. But that's it for B. Oh, sorry, A. Any question for A? All right, so let's do B. So for B, so what sample size should be obtained if she wishes the estimate to be within 2 percentage points with a 95% confidence, assuming that the data is normally distributed, but she does not use any prior estimate. So in this case, she's not going to use the 0.98 or the 0.992. So we're not going to use that. So this one, we don't know that information. So since we don't know that information, instead of using the first formula, we're going to be using this formula over here. So we're going to use n is equal to n1 is equal to n2 is equal to 0.50 times Z alpha divided by 2 over margin of error squared. So for this one, it should be much, much easier because for this one, fortunately for us, we don't have to do this part. All we have to do is do 0.50. Since we have the same confidence level, it will still be 1.96. My margin of error is still 2%, so 0.02, and we square it. So I could trust you, you could do that in your calculator. So do 0.50 times 1.96 divided by 0.02, and you take that to the second power. If you do this one in your calculator, you should get 4,802. So if you look at this one, this is telling you like, if we don't use any of the prior estimate, we need a sample size of 4,802. So that's why it's important if you could find a prior estimate, it should pretty much help you out because it's going to tell you, hey, you don't need as big of a sample size. Because if you go into it without knowing any prior estimate, it's going to tell you need a big sample size. But if you do have a prior estimate, like in part A, that's going to minimize how big of a sample size you actually need to get for both populations. But that's it for B. Any question in regard to B? Yeah. All right, let's go on down. All right, so up next we're gonna do 11.2. So 11.2 is for dependent data set. So for this one, it's gonna be, we have two mean, or we have the inference of the two mean, but the thing is our data set are dependent. So that means the way I choose one group influence the way I choose the other group. So it's either gonna be like a before or after, or it could also be like a match pair design. So for this one, you have to know it should be a dependent data set. So for this one, it's going to be a little bit different. Okay. So for this one, if we're doing a match pair, for a match pair, the central limit theorem applied to this one. So for this one, we're going to use the central limit theorem that n has to be greater than, or it has to be equal to 30. So n has to be greater than or equal to 30, for that way the central limit theorem can apply for this problem. All right, so for this one, it's a little bit different because we're not going to be computing the mean of each group. What we want to do, we want to compute the difference of each group, because say if we're doing it before and after, we don't care about the before score or the after score. We just want to see how much of an improvement or how much of a disimprovement you were. So say in the before you score a 3, and the after you score a 7, well, what we're going to calculate how much did that person improve. So instead of getting 3 and 7, what we're actually going to do, we're going to get 5, we're going to get 4. Because if you do 7 minus 3, you get 4. So in this chapter, we're going to be focusing on something called D bar. So the D bar is the average of the difference of the two data sets. So once we get the difference from each data set, we're going to get the average of it. And we're also going to get the standard deviation of that data set. It's actually going to be pretty easy the way to get it, because we're going to use our calculator to do that for us. Any question for D bar? All right, no question. All right. So for this one, these are going to be my 3 null and alternate hypotheses. So let's kind of look at the null hypothesis. So it says mu of D bar is equal to 0. So if you notice for all of the null hypothesis, it states the same thing. Mu of d bar is equal to 0. So you might be wondering, like, why is it equal to 0? So if you remember for the null hypothesis is stating there is no change. So say in the before test, you got a 5. And in the after test, you got a 5. So pretty much this is stating there is no change. So if I take the difference of these two numbers, so we'll say the difference is equal to 5 minus 5, which you get 0. So that's why the null hypothesis is mu of d bar, which is the mean of the difference, is equal to 0. Because if it is equal to 0, that's telling me from the before and after, or comparing these two different groups, there is no difference. The alternate hypothesis is stating there is a difference. So we're either going to state it's not equal to, is less than, or is greater than. So the two that you kind of want to keep your eye on are the less than and the greater than. Because technically, depend on how you subtract it. So you could either do before minus after, or you could do after minus before. Yeah. So depending on how you subtract those two values, it will change your alternate hypothesis. If you do before minus after, for that one, you might have to put less than. But if you do after minus before, that one will be greater than. So you just kind of know, depending on how you subtract it and how you get the difference, that's going to pretty much dictate what your null and your alternate hypothesis should be. Everybody good with that? All right. So here is the formula we're going to be using. If you notice, we're using t distribution again. So for this one, in our calculator, we're going to use the t-test. So if you look at it for the t-test, let's say you're going to get the mean of the difference. You're going to divide it by the standard deviation of the difference. And then we're going to divide that by the square root of n. So for that one, hopefully it shouldn't be that bad. Any question in regard to that so far? Sweet. All right, no question. All right, and also just remember for this one, we're going to be using the degrees of freedom. So for degrees of freedom is essentially you look at the difference, you see how many numbers do you have in the difference, and you subtract it by 1. So if you have 10 before and after, you do 10 minus 1. So we're going to go ahead and we're going to do this one problem, and then we'll call it a day for today. All right, so for this one, what we want to do, we have quiz versus lecture post rate. So what we're trying to do is that do you think your post rate is higher when you are taking a quiz than when you are sitting in lecture? The data in table 2 show post rate collected from 10 students in a class lecture and then from the same student during a quiz. Assume that the data has a normal distribution. So we already know the normal distribution. So if you look at this one, this is the before and after, because essentially what we're doing, we have the same student, but what we're doing, we're testing their post rate when they're taking a quiz, but then we do it again when they're taking a lecture. So we're using that one student to collect 2 data sets. Right. So that's why this is dependent. All right. So for this one, how many total students did they get? Cool, thank you. So they got 10 students, so we had 10 students that were randomly selected. So what we want to go ahead and do, what we're going to do, we're going to first do check the assumption. Or yeah, let's check the assumption. For this one, we'll go in order. So that way it won't be confusing. So for this one, do I have to check the central limit there? Or is it okay for me to essentially skip checking the central limit there? Is it absolutely necessary to check it? And the answer is no. So if you look at it, it tells us our distribution comes from a normal distribution. All right, so that's it for that. So in a sentence, describe the parameter that being tested. So the mean score, or no, mean post rate during lecture and during a quiz. So that's what being tested, the mean post rate during lecture and during a quiz. Let's see if I can do this. All right, let's go. All right, so the first thing I want to go ahead and do, we're going to go ahead and subtract this. So for right now, what you want to do, you kind of want to figure out if you want to do quiz versus lecture or lecture versus quiz. So for this one, when do they think we're going to have a higher post rate? Cool. So they think we're going to have a higher post rate when we're taking a quiz. So they think the post rate of the quiz should be bigger than when it's in the lecture, correct? So if they think the post rate should be bigger when it's lecture, what we're gonna do quiz minus lecture. Because if that's true, then you get a positive number when quiz is bigger than lecture. Because the only way to get a positive number is the quiz post rate has to be bigger than the lecture post rate. But if they get a negative value, a negative means the quiz post rate is actually smaller than the lecture post rate. So when you're choosing which one to choose, you kind of have to also factor in like, okay, when do I get a positive number? When do I get a negative number? You get a positive number when the quiz post rate is bigger than the lecture post rate, but you also get a negative number when the quiz post rate is smaller than the lecture post rate. So now that we decided that, let's go ahead and subtract these. So if I do 75 minus 73, you get 2. 52 minus 53, you get negative 1. 52 minus 47, you get 5. 80 minus 88, negative 8. 56 minus 55, you get 1. 90 minus 70, you get 20. 76 minus 61, you get 15. 71 minus 75, you get negative 4. 70 minus 69, you get 9. 68 minus 78, you get negative 12. Okay. Any questions so far how I got those numbers? All right, so let's do the interesting part. Let's do our null and alternate hypothesis. So the null hypothesis should be very simple. Null hypothesis is that the difference, well, there is no difference between the before and after. So there is no difference between the post rate when they're taking a quiz or the post rate when they're taking the lecture or when they're sitting during lecture. So for this one, we put mu of d bar and we'll put 0. So for this one, what you have to do, you have to look at the plus or minus. So if you look at it, we want to prove that when they're taking the quiz, their post rate is higher than the lecture, correct? All right, everybody said correct. So we want to prove that the quiz lecture post rate is, well, the quiz post rate is higher than the lecture post rate. So what we have to do, we have to decide whether if I put a greater than or a less than. So a greater than, so if I put, it should be greater than 0, which number are greater than 0? Or which type of number are greater than 0? Well, if you look at which type of number are greater than 0, thank you, is positive number. So if we want to get a positive number, we put greater than. But, so we'll put positive right here. But if we want to get a negative number, we put less than. So if you look right here, we said quiz is greater than lecture, we get a positive number. So in this case scenario, we put positive. So we want to say the mean difference or the mu of the difference of the mean is greater than 0. Because if it's greater than 0, that means that the quiz post rate was bigger than the lecture post rate. So let's go ahead and do this next part. So for n is equal to 10. Degrees of freedom is equal to 10 minus 1, which is 9. Right here where it says the difference, well, this is technically what you want to put. Copy. Everybody good so far on 1 through 4? So the next part, we're gonna let the calculator do the work for us. Because the calculator gonna pretty much, if you look at this, this is our data. So we're gonna enter this into our calculator as our data. So you should get a head start on me. And you want to start putting this into your edit list. So I'm gonna go to stats, we're gonna go to edit. I'm gonna go to L1, delete all of this. I don't want it, I don't need it. So we put 2, negative, 1, we go 5, we go negative 8, you go 1, you go 20, you go 15, you go negative 4, you get 9, and you get negative 12. So that's what you want to enter into L1. Any question on what we enter in for L1? All right, so now what you want to do, you want to go to stats, you want to go to tests, and we're going to do a t-test. So for this t-test, we're always going to use data because for this one, you're always going to have to calculate the difference of it. So you do data because I wanted to look at L1. So for this one, if you look at it, it's asking me for what is mu. So for this one, mu is actually is equal to 0. Okay, if you look at your null hypothesis, we say mu of the mean of the difference is equal to 0. So that's why this is equal to 0. So now we go all the way over here. We put greater than because that's our alternate hypothesis. And we go ahead and put calculate. All right. So if you look at it, it said the mean of x is equal to 2.7. So that's d bar. If you look at it, give me s of x, which is the sample standard deviation of the difference mean, which is equal to s of d, is 9.9. I'll leave it at that. If you look at the very top one, give me t, which t is 0.8595. But also, if you look at it, it gave me p-value, and it gave me p-value of 0.206. 0.206. Sweet. So if you look at the calculator, that all of that worked for us. Any question on how to get this? All right, so let's go back to the notes. Let's finish this up and let's call it a day. All right, so if you look at number 5, for D bar, I put 2.7. For SD, I put 9.9. For T, I put 0.8595. And if you look at part 6, I put, this is a right tilt test. I put 0.206, and I put p-value 0.206. For this one, what was our, what you want to call it? What was our alpha? Oh, 0.05. So if you look at it, it's 0.05, so that means p-value is bigger than alpha. So for this one, we'll say we fail to reject. So we'll say there is no difference. Oh, sorry. There is not enough evidence to support the claim that the post rate for quiz is higher than the post. And that will be it for that one. Any question in regard to the last problem? Cool. All right, so that's it for today. So stop share. We'll stop recording.